All right. Good morning, folks. Let's go ahead and let's get started. Just make sure if you have any questions about what we've done up until this point and what we will be doing in the lesson today, and please stick around on Monday after I take roll and get some extra help with it. Okay. So, because what we'll be talking about today after we go over the last structure that I left you with on Thursday, yeah, on Thursday's lesson. We're going to get into the theory behind bonding. Specifically, we're going to take a look at what's called the localized electron model. And so what we'll do then is I'll use that to help you understand how these bonds actually form. What we've been doing is we've been drawing structures, and I've explained to you that you have the sharing of electrons between atoms, either 2 or 4 or 6. And so that was basically it. I mean, we know about the electrons being shared. That's what a covalent bond is. We've talked about how the atoms are grouped together, the connections that are made. So that we do know. And what we're going to be doing is we're going to take what we know about that. We're going to take that information, that knowledge, and then apply it then and talk about how these bonds form. That's what the localized electron model is. And so it gets a little bit, we go back a little bit into the discussion of quantum mechanics that we had back in chapter 5. And so if you need to, you may want to go back and refer to chapter 5 and take a look at what the orbitals are, the atomic orbitals, the S, the P, the D, and the F orbitals, their shapes, because we will be dealing with that a little bit more in this discussion today. And then hopefully my hope then is that after the lesson today on Monday, what we can try to do then is get into VSEPR theory so that Tuesday then we can do the PhET lab. Okay, so fingers crossed. Hopefully that's where we'll be going with this. Okay. So let me go ahead then and let me share with you my screen. And let's take a look at the last shape here that I asked you to draw. And so remember, what we did here is we were looking at the exceptions to the octet rule. So we had we have molecules then, molecular compounds that will form that will not adhere to the octet rule for one of 3 reasons. Either you have an odd number of electrons, odd number of total electrons like we have here for nitrogen dioxide, and we saw that on Thursday, or we have then a center atom that will not have enough valence electrons to get to 8, and so it will be deficient in electrons. Okay, and so that means it'll have less than 8, like we saw then with boron trifluoride. And so with phosphorus pentachloride, we get a chance to take a look at the third possible way that the octet rule is violated when it comes to molecular compounds. Okay, so let's go ahead and let's take a look at phosphorus pentachloride. Let me go ahead and open up a whiteboard here. Okay. All right, and let me share this with you over here. That ways. Okay. All right, so phosphorus pentachloride. Let's go ahead and let's take a look at this here. And again, we have we're going to have then 1 phosphorus and 5 chlorines. Hopefully, you all recognize then. Hopefully, you're getting to the point where we're starting to recognize which atoms are going to could potentially be center atoms and which atoms cannot. So hopefully you recognize then that phosphorus will have to be the center atom here. Okay, this is the Lewis dot structure for phosphorus. Okay, chlorine cannot be the center atom because it, like hydrogen for the most part, can only form a single bond. So I'm going to go ahead and I'm going to connect it right here. So we have then. Oh, sorry. Let me go ahead and do this here. We have a single bond here. Okay, so that's 1 chlorine. And then we take a look at the other chlorines. And we see then that at least for 2 more chlorines, and possibly, I'm sorry, okay, and 2 more chlorines. So you have the second chlorine coming in here, forming that bond over there with a lone unpaired electron here for phosphorus. And we see then that would also be true. That would also would happen with the third chlorine there. So 3 chlorines potentially could bind to phosphorus in making 3 single bonds. And what you notice here then is, if this is the case, then all the atoms involved, excuse me, all the atoms involved will have their 8 electrons. Okay, so each chlorine will have their 8. Each chlorine will have their octet, and there it is. And here, phosphorus at this point, phosphorus also has its octet. But the problem that we have right now then is that this compound is not phosphorus pentachloride. This compound right now is phosphorus trichloride. And what we want to do is we want to find out how the phosphorus pentachloride, okay, how this compound forms. What's the bonding there? Okay. All right. So what we could now, hopefully you can see that that we can. There is an option that some folks take, and they think then, well, why can't we just take a chlorine here and have a coordinate covalent bond form between phosphorus and that chlorine right there. Okay. The problem with this, then, I hope you can recognize this, then, is that that can't happen because then you have three bonds forming here. So this cannot form. Phosphorus cannot take its lone pair here and form an electron with chlorine. That cannot happen because chlorine cannot accommodate these two here. So you won't get a coordinate covalent bond forming there. That won't happen. And furthermore, that would only allow you to have 4 phosphorus connected to four chlorines bonded to the phosphorus. Okay, so that cannot happen. Okay, what happens here, and we talk about, and we understand why this, and remember, we're learning how the connections are made here, but we don't know the why. But we will learn why in just a moment. Phosphorus does this. It takes those two lone pairs, and that one lone pair, and it splits it up. It's able to split it up because of a process known as, again, hybridization. I had mentioned that term, hybridization, last week. And so what happens then, when phosphorus, when it needs to, or what will happen is it will hybridize, okay, forming molecular orbitals, and what it'll do then is it will place electrons in those molecular orbitals. And so therefore, when this happens, then what you're going to see then is that these electrons here split up as well. So that the electron pair splits up as well. And there it is. That's how we can form then the compound here called phosphorus pentachloride. The phosphorus pentachloride then is comprised of 5 single bonds. Okay? 5 single bonds that connect these 5 chlorines to the phosphorus. Okay? And if you notice then, if that does happen, phosphorus goes way over, or it goes over the octet rule. It has here 10 total electrons, 2, 4, 6, 8, 10. Okay, and so therefore phosphorus in the compound phosphorus pentachloride has violated the octet rule. In the compound phosphorus trichloride here, it does not violate the octet rule. It actually adheres to the octet rule. But phosphorus is able to move beyond and add more electrons because it has what we call these hybrid orbitals to accommodate that. Okay? Not all atoms can do that. Okay, and I'll give you a list in just a moment of the atoms that must adhere to the octet rule. Okay? But the other non-metal atoms, they will be able to. So outside of the list that I'm going to give you in just a moment, now that we know about exceptions, okay, the potential exists for atoms to either have more than the octet, like we have here with phosphorus, or less than the octet, like we had with boron. Okay. All right. So with that said, then 1, 2, 3, 1, 2, 3, 4, 5. We have 15 electron pairs there. Let's go ahead and just finish this up here. 15 lone pairs. Okay. In this 1, 2, 3, 1, 2, 3, 4, 5. Okay. All right. So that's what we have then for phosphorus pentachloride. Okay. So the question then is this: okay, do all non-metal atoms, are all non-metal atoms capable of violating the octet rule? The answer there is no. Okay. The reasons why it's a little bit more complex than what we need, what we can go over here in class. But what I will do for you then is I will give you a list of atoms that must adhere to the octet rule almost all the time. Okay, so let's go through the list here. We have carbon, oxygen, nitrogen. Okay, and then we saw then, and I'm going to put an asterisk here by nitrogen, because we saw then that when nitrogen is involved in an odd number, a molecule with an odd number of valence electrons, okay, then it can violate the octet rule. But outside of that, it has to adhere to the octet rule. So carbon, oxygen, nitrogen. Okay, we have then all the halogens. Oh, sorry, fluorine, chlorine, bromine, and iodine, for the most part. Okay, so these atoms right here, so these elements right here, so the ones I've listed here for you, okay, these must always adhere to the octet rule. They must follow the octet rule. They will never violate the octet rule. Okay, again, with the exception of nitrogen, when nitrogen is part of an odd number, a molecule with an odd number of valence electrons. Okay, so keep these in mind right here. So basically, just all the halogens, carbon, oxygen, nitrogen. Whenever you see those elements in a compound, whenever you see those elements in a compound, they must, first and foremost, you got to make sure that you assign them their octet. Every other element then can either violate or can violate the octet rule by either having too little or having too many electrons. Okay, so but these 7 right here, you got to make sure then whenever you see them in a molecular compound, you have to make sure you assign them their 8 electrons. Okay, and then you can work from there. Okay, all right. Hopefully you got that. I'll remind you of that again as we go forward with this, but make sure you keep that in mind. Okay. All right, let's go ahead then. And that's it. Now let's move forward. That is it for the structures, basic discussion of the structures. What I'd like to do then is let's go ahead and let's dive into bonding theory. Okay? Because bonding theory then, and again, I'm going to focus in on localized electron model here because we have molecular orbital theory as well. But we'll talk about that. You get to talk about that for those of you folks who are moving on in the later class. Okay? But what we're going to do here is we're going to look at what's called the localized electron model and explain them how the electrons are shared. So we know the way that they situate themselves. Now we're going to understand the reason why certain atoms are able to violate the octet rule and why electrons are being shared and where they're being shared within the space between the atoms as well. Okay, so we'll talk about that. And then we'll get to what's called VSEPR theory, and that's where you will learn about geometry, the three-dimensional structure of molecules. Okay, and then what I want to do then is I want to talk about those hybrid orbitals. So I'm going to introduce these to you first, and then we'll talk about those as well. Okay, all right. So the key to understanding what molecular orbitals are, is to understand and remember what the atomic orbitals are and what purpose they serve. Remember back in chapter 5, the atomic orbitals represented the regions of space. Okay? They represented the regions of, physical space, but also more importantly, the energetics of an electron. Okay? So therefore then, with an s orbital like I have here, the s orbital represented a probability of finding an electron at some point around the nucleus. And s orbital represented then the lowest energy of all the atomic orbitals. And so remember, we had then think back to Bohr's model of the atom, where we had the circles around the nucleus. Those represented principal energy levels. And then within each principal energy level, you can subdivide those principal energy levels into orbitals, okay, into sub energy levels as well. And so that's what the atomic orbitals are. And within those atomic orbitals, we can find the electrons. And so the electrons then are the orbitals, atomic orbitals represent the location, if you want to think about it that way, of the electrons around the nucleus, around a single atom. Okay? So what happens then when those atoms start interacting with other atoms? Okay? And so the quantum mechanics can also be used to explain how that happens. And so we apply then quantum mechanics to bonding. And so we come up with this quantum mechanical model of bonding, and that's what the localized electron model, that's what the molecular orbital theory is all about. Okay? And so essentially, the way that you want to think about it is this. Okay? You have the atom, okay, and it has its atomic orbitals. Okay? When it gets together with another atom and it wants to share its electrons, what the atom has to do then is it has to take its atomic orbitals and change them. Change them so that it can now go ahead and share its electrons with the other atom coming in. And both atoms then will change their atomic orbitals. So when the atom's all by itself, it has atomic orbitals. When it gets together with another atom to bond, it changes those atomic orbitals into what we call then molecular orbitals. Okay? And this only occurs when the atom is involved in a molecular compound, when it is bonding with another atom. Molecular orbitals do not exist. So what we'll be talking about in just a moment. Okay? Molecular orbitals do not exist when the atom is all by itself. Okay? When the atom is in its elemental form, it does not exist. Okay? Now, the exception to that rule then would be when you have diatomic elements. Remember, hydrogen, there are certain diatomic elements you have to remember: hydrogen, oxygen, nitrogen, all the halogens. Those are diatomic, which means that those are compounds. Those are molecular compounds. And so they will hybridize in order to form those bonds. Okay? Now, hydrogen is an exception. We'll talk about that later, but just keep that in mind. Okay. All right. So let's talk a little bit more about these molecular orbitals and some of the characteristics of these molecular orbitals. Okay. So like I said, then the molecular orbitals only form when the atom joins together with another atom to form a molecule. Okay. Now the molecular orbitals, each atom will hybridize. Each atom will form these molecular orbitals, and the interaction of those molecular orbitals is what we refer to as bonding. And so there's two types of bonding. Okay, we have sigma and pi bonding. I'll talk about that a little bit more after we discuss molecular orbitals. But what you need to make sure you understand is that the rules that we used to discuss the atomic orbitals also apply to molecular orbitals. You'll learn this a little bit. You'll learn this later in later class. But the Aufbau principle, the Hund's rule, and the Pauli exclusion principle also apply to molecular orbitals, and they do. And we're going to go over that a little bit once we talk about the bonding types of the sigma and pi bonding. Okay, but understand then that these molecular orbitals, those are the ones that the atoms use to bond. So they are also referred to as bonding orbitals because the molecular orbitals get together, they interact with one another, the electrons are being shared, and that is the basis of the covalent bond. Okay, the basis of the covalent bond then is molecular orbitals forming in each atom. The molecular orbitals interact with one another, and then the electrons are able to move across from one side of the atom to the other, from one atom to the other, across these molecular orbitals right there. Okay, and so that's what you need to keep in mind as we go through this. Okay, all right. So these molecular orbitals that form, okay, what we refer to then, we'll talk about these. They have to undergo what's called a process of hybridization, and so we refer to them also as hybrid orbitals as well. Okay, and so these hybrid orbitals then they're going to situate themselves around the atom in a three-dimensional way, in much the same way then that the atomic orbitals, remember, they also situate themselves around the nucleus in a three-dimensional manner. Okay, the hybrid orbitals, these molecular orbitals, do the same thing. Okay, and so we can use VSEPR theory, which is valence shell electron pair repulsion theory, to explain then how these hybrid orbitals, or how these the shapes of these orbitals as they sit around the nucleus. Okay, all right. And so with that said, then this valence bond theory, this is also what's known as the localized electron model. Okay, so let me go ahead and write this down. So valence band theory is also known as localized electron model. That in there. Remember this. This is also known as localized, and you'll see this electron model. Okay, and it helps us to explain then how these bonds form. Okay, all right. So when we talk about hybridization, okay, again, what happens is that the atomic orbitals do is they get together and they change. Okay, so an S will pair up with a P, okay, and it will change. Okay, an S will pair up with a P and a D, and it will change. Okay, to form what are called equivalent hybrid orbitals. Equivalent meaning then that they are equal. They are exactly the same. They look exactly the same. They will be actually they have the same energy as well in a process that we in a phenomenon that we refer to later on as the term escapes. Sorry, you guys. Degenerate. I'm sorry. That's what I get for getting old. Okay, but in a term that we refer to as degeneracy, and so we'll talk about that as well in a little bit as well. Hopefully, we can get to it. Okay, but and so that's what we have there. And then the last thing you want to do then is remember then that the number of hybrid orbitals, since we are forming them from the atomic orbitals, will always be the same. When they combine together, the number of hybrid orbitals they get together, the number of atomic orbitals they get together to form the hybrid orbitals, the numbers will be exactly the same. And again, doesn't make too much sense right now, but bear with me just a little bit. I'm going to show you in just a moment how this works. Okay. All right. So keep in mind then that when these hybrid orbitals form, when hybridization occurs when atomic orbitals blend together to form these molecular orbitals. The molecular orbitals then will all be degenerate. That means they will be equal in energy. And also the number of hybrid orbitals that form, the number of molecular orbitals formed will be equal to the number of atomic orbitals that got together to form, to make them. Okay? All right. There are going to be 3 types of hybrid orbitals. There are many types of hybrid orbitals that we'll talk about. Okay, there will be many types of hybrid orbitals that we will talk about. Okay, that exist that we deal with in chemistry. But we're going to focus on 3 in particular. In this class, then we're only going to focus on 3 in particular. The hybrid orbitals that we will be talking about. And I will show you then are what are called sp3 hybrid orbitals. Okay, sp2 hybrid orbitals. And sp hybrid orbitals. So those are the 3 types of hybrid orbitals that we will be I will be teaching you in this class here. And again, there are others. There are sp3ds, sp3d2s, and so forth and so on. But we don't, for this class here, we're going to keep it very basic, and we're just going to talk about how these 3 hybrid orbitals form. Okay. All right. Let's go ahead then. And let's take a look at the let's take a look at sp3 hybrid orbitals first. Okay, so let me go ahead and put this out. Okay. All right, so sp3 hybrid orbitals, we start out with them, and you can kind of think of this as a process. Okay, you have an atom here. So let's say this is a carbon atom. Okay, so we have a carbon atom right here. Okay, and the carbon atom here is going to have an s orbital and p orbital around it. Okay, remember carbon atom. Let's go ahead and let's stick with carbon. Carbon then, electron configuration for carbon is 1s2, 2s2, 2p2. Okay, yeah, 1, 2, 2p4. Sorry. Okay, so the 2p2. Hold on a second. Sorry, guys. Let me check something really quickly. Let me grab my book here. 2p2. Sorry, you guys. Okay. So if you notice here, we're not for the purposes of hybridization, we don't look at the core electrons. The only orbitals that hybridize are the ones that contain the valence electrons here. So there's where we have then the 4 electrons there. So that's the s orbital that we're referring to here. Okay, so we have 1 s orbital and 3 p orbitals here. So make sure you understand then, and this is going to be true for any atom. The only orbitals that hybridize are the orbitals that contain the valence electrons here. So these are the valence electrons here. Okay, and so those are the s orbital here. That's the one that's the s orbital, not the. And I'm sorry, this sometimes is confusing. This is not referring to the 1s orbital. Okay, what it's saying is that we're taking 1 s orbital and the 3 p orbitals, and we hybridize them. That's what you want to make sure you keep this in mind. Okay, so what carbon will do then, it's going to take these 2 orbitals right here, and it's going to hybridize. Okay? So how does this hybridization process work? Okay? Basically, what we do then is we blend together the one of those s orbitals here. So remember, s orbitals only have one shape, only one shape here, and we're taking all 3 of the p orbitals that comprise the orbital that we call p orbitals, and we blend them together. This is the process of hybridization right here. We hybridize them, and when we hybridize them, we form new orbitals. Okay, and if you notice here, the new orbitals here have a little bit of the p and a little bit of the s in them. Okay, and so we have then all 4 of these are exactly the same, and that's what I was pointing out to you in the previous slide. Then that all of them are equivalent. Okay? So we have then 4 equivalent. So these are all equivalent structures here. So we have 4 equivalent, which means that they are identical orbitals. Okay. So they look the same. They will have the same energy as well. Okay, but that's what we have right there. We have 4 equivalent. We go from having 1 s and 3 these p orbitals to getting 4 of what we call now sp3 hybrid orbitals. So these 4 here are what we refer to as sp3 hybrid orbitals right here. Okay, and the reason why they are hybrid is because we hybridize. We take the s and we get the p and we mix them together. And when we mix them together, we get these 4 here. Okay, and again, a little bit of p, which you see here, and a little bit of s, which you see here. Now, we don't see them, remember with the p orbitals, we don't see them just kind of lying flat like that. We see them kind of centered around the nucleus. And that's what exactly happens here. So these 4 hybrid orbitals now will situate themselves around the nucleus. So if you can imagine, the nucleus of the carbon atom is right in here. The nucleus of the carbon atom sits right in here. There's where the nucleus of the carbon atom is. That's where the protons are sitting. And these hybrid orbitals here will situate themselves in a 3-dimensional way around that nucleus. Okay, so here is the nucleus of the carbon atom right in the center of those 4 hybrid orbitals right there. Okay? And so we refer to this then as sp3 hybridization. Okay, and so what will happen now then is, remember, and let me go ahead and draw the picture for you. Remember with the s orbital here and the p orbitals and how these electrons spread out. Let's go ahead and do that really quickly. Okay, so this is your s orbital, and here are the 3 p orbitals right here. 1, 2, 3. Okay, and so with the electrons, remember, electrons in, 2 electrons in the 1s orbital. Okay, okay, and 2 electrons in the 3p or in the 3 orbitals. Okay? And that's where we get then that the, remember with carbon, with the when we did the Lewis dot structure for carbon, we drew then carbon. This is atomic carbon now with 1 pair and 2 lone pairs. So this is atomic. This is carbon as an atom. Okay? So this is the carbon atom right there. All right. Now, though, once we fill it in, these 4 electrons then, applying Hund's rule, and again, these 4 hybrid orbitals are what we refer to as degenerate. Okay, and so we'll talk about what degeneracy is a little bit later. Okay, so these are degenerate, meaning then that they are all equal in energy. And remember, with Hund's rule, when we have that, if the electrons can spread out across an equal area here, they will. So therefore, what happens then is that these 4 now, before they were not degenerate, remember the s orbital is a little lower in energy than the p, so that means then the s orbitals fill in first, and that's why the p's fill in here. But now that we have the hybrid orbitals, these 4 electrons can all spread out because all 4 of these hybrid orbitals are degenerate. Okay? And that's why when we drew the Lewis dot structure for carbon, remember, and when they bond, we took the 4 electrons and we spread them out. So therefore, this carbon atom here is the carbon atom that we see then when it is part of a molecule. I'm sorry, so this is atomic carbon. This is going to be molecular carbon, meaning this. The carbon that you see on the left here then, that's the carbon when it's all by itself. It's not bonding with any other atom. That's why it's the atomic, and I should put this in quotation. This is the version of carbon when it's all by itself as an atom. This is the version of carbon when it is part of a molecule, and thus I call it molecular carbon. Okay? Because this is the way that the electrons are going to split up when carbon hybridizes and gets ready to bond. Okay? And so what you can imagine here then is that, again, these don't sit out on their own. They sit in, there's the nucleus. What will happen then is that the electrons then will sit there, 1, 2, 3, and 4. And this is what we refer to as a tetrahedral geometry. Remember, this is not a 2-dimensional surface here. You can imagine then that This one's coming out at you. These two are at a right angle, or not quite a right angle, but these are at an angle with each other on the plane of the paper, and this one's going behind the paper. This is why we will do the VSEPR theory. This is why we're going to do the PhET lab, hopefully on Tuesday, to get you to see then the three-dimensional structure here that's formed by these sp3 orbitals right here. Okay? And so that's why we have this. So this is our two-dimensional representation of molecular carbon, and that's what we have here. And this is our two-dimensional representation of atomic carbon. Okay, this is the carbon right here. This is the form of carbon right here that bonds with other non-metal atoms to form the covalent bonds and the molecular compound. Okay, so please make sure you keep this in mind as we go through this. And if you notice, then there are 4 locations here. So this this carbon then can form potentially 4 single bonds. Okay, all right. That is sp3 hybridization. Okay, let's go on then and let's take a look at the next form. Okay, all right. I'm sorry. So here it is. We have sp3 hybridization. Sorry, I want to go 4 sp3 hybrid orbitals. Okay, we formed that. These are all equivalent to one another. Some folks have often told me that these sp3 hybrid orbitals look like drumsticks. I suppose if that helps you remember them, that's all good. Okay, all right. So what we typically will see then, and like I pointed out to you, when these sp3 hybrid orbitals do form, they will be involved in forming single bonds. Okay? And keep that in mind right there, because that will help you understand this. Okay, so they will always be involved in forming single bonds. Okay? So sp3, whenever you have that, you're going to form then 4 single bonds, okay? And they will always be involved in compounds that only have single bonds. Okay. All right, so make sure you keep that in mind, because when we move on and we try to use this, that will be very helpful for you. So sp3 hybrid orbitals always form single bonds. Okay? They will form single bonds. They will be used to form single bonds. All right, let's go ahead then and let's take a look at the next type of hybridization. So we've talked about sp3 here. We also have sp2. Now, I'm sorry, one thing I probably should have pointed out to you earlier is that if you notice here, we start out with 4 total orbitals here. Okay, so if you take a look at this here, we started out with 4 total orbitals here. Okay, so we have one s orbital and 3 p orbitals, 4 total atomic orbitals. These are atomic orbitals. If you notice here, we end up with 4 total hybrid orbitals or molecular orbitals. So that has to be always the same. Okay. All right. So make sure you keep that in mind. Okay. So with sp3, then we form with sp3 hybrid orbitals, then we will always get 4 of those hybrid orbitals. Okay. All right. Let me go ahead and save that one as well. Okay. All right, so let's go ahead then and let's take a look at sp2 hybridization. Okay. All right, now sp2 hybridization is still involves an s orbital and p orbital. Okay, and so make sure you keep that in mind. So you still have s orbitals interacting with p orbitals. Okay, but what you're going to notice here, and I want you to draw your attention to this again. So we take the s orbital here. Whoops, sorry. And if you notice then, what we do then is we combine it with only 2 of the p orbitals. So we take the 1s and we combine it together with 2 1s, the s orbital. So we take the s orbital and we combine it together with 2 of the p orbitals right there. And if you notice then, what do we form here? And there it is. We have the same kind of shape there. These are our sp2 hybrid orbitals right there. And so if you notice then, same thing with these sp2 hybrid orbitals, which only requires 3 atomic orbitals. Okay, we're only going to take 3 atomic orbitals here. And then we form then 3 molecular orbitals, these hybrid orbitals here. We end up with 3 hybrid orbitals. Okay, I'll talk about this one in just a moment. Okay, but that's the combination right there. We're taking the s orbital, okay, and this time we're going to combine it together with only two of the three p orbitals, and we get then three sp2 hybrids, hybrid orbitals. So we hybridize here, but this time instead of hybridizing all of the p orbitals, we only take two of the p orbitals and we hybridize them. Carbon only, or I'm sorry, the atom only then takes two of the hybrid orbitals and hybridize them there as well. Okay. So I'm out of time here. So what I'd like to do then is on Monday, so we're gonna I'll finish up here with on Monday then. We'll talk about how this works and what does this unhybridized. So this is an unhybridized p orbital. What does it do? Okay, so we have then three sp2 hybrid orbitals, and we have one unhybridized p orbital. We'll take a look at that on Monday, and we'll see what happens here. Okay, all right. So please take a look at section 8.2 in your book, okay, and look through it. And this is not easy stuff. Okay, and I don't I won't kid you about that. Okay, so this is difficult. This is fairly challenging, but you can work through this. Okay, and so we're looking back into physics again. We're delving into physics again. I know it's a little bit more difficult, but I think in the end, if you kind of understand, mixing together, hybridization, and what gets hybridized, which atomic orbital gets mixed, at that point, then you will be able to differentiate and distinguish between the three different types of hybrid orbitals. Okay, we've talked about sp3, we're talking about sp2 now, and then when I introduce sp to you on Monday, okay, you're going to see then that the difference in the different hybrid orbitals is going to be how many of the atomic orbitals actually mix together. Okay, but in terms of their function, okay, they pretty much still function the same way. Okay. All right, very good, folks. We'll pick up with this discussion on Monday. Okay. Have a good rest of your day. Have a good weekend, and I will see you. And hold on, let me save this real quick. I will see you on Monday. Please remember to stick around on Monday after class if you have any questions about this, and that way then I can help you go over a few of these items here. Okay. All right, very good, folks. Have a good rest of your day. Have a good weekend, and I will see you on Monday.